So thanks, Or, for the kind introduction. So as you said, today I'm going to talk about how to build the foundation model in 4D, and in particular using the LiDAR sensor. So first of all, the question is a bit like, why do we need that, right? Like, what do we want to do with this type of generation? So here's an example demo of what we would like to have as an output. We would ask our system to segment, in this case, fire hydrants and trash cans, which are kind of open vocabulary objects, right? I mean, they're not like your typical cars and bicycles that you find in AV settings. And you can see here how it is highlighting these objects. In orange, the fire hydrant, in blue, the trash cans, and it's highlighting them directly in the LiDAR space. And so we would like to do this virtually for any object in the scene. So we started this a couple of years ago. So now we have built kind of several pipelines that feed into what we call the SARL-verse. And I'm going to talk about the four main ingredients of our foundation model and how we build up step by step. So, okay, the first work was the segment anything in LiDAR, the SAL work, which gives the name to the whole SAL-verse, in which we basically want to do open vocabulary classification and localization. Wasn't it? And we do this for a single scan, right? In a second step, we want to extend this to full LiDAR sequences, right? So we not only want to do detection, but we want to track the dynamic objects and obtain a consistent output for the full temporal sequence. The next step then would be what happens when you don't fully see the object, right? So if you are familiar with LiDAR scans, especially from AV, you almost never see the full extent of the object, so you get these partial reconstructions. So the next step is to actually do an A model prediction, so basically to work on scene completion. And the final one would be to actually make this a foundation model, right? Like work on scale, large-scale data training, and cross-sensor generalization. So let's go step by step. The first three parts, they have two key ingredients, each of them. One is going to be the data engine, and the second one is going to be the model, right? So how do we obtain the data to train each specific model? And I'm going to talk about this for each of these parts. So, okay, let's start with the first one, Sal. So essentially our goal is to get a LiDAR point cloud as input and a series of text prompts. And then our model should give us as output the instances and semantics. So basically it should learn to segment and classify any object. Now, we know from the 2D world that this is very possible in a fully supervised way. You just get a bunch of data annotated and there you go. But doing this by manually annotating large-scale data in 3D, and especially when thinking about going to 4D, this is actually very painful, right? So we would like to really bypass this. And so instead of annotating data in 3D, we say, how about we benefit from existing 2D foundation models? Like how far can we push this with 2D foundation models? So as I said, like there are two ingredients to each of the works. Like one is the pseudo label engine, right? In this case, like in the case of SAL, we want to know how to transfer the information from 2D foundation models. In our case, we'll be using CLIP and SAM into the 3D world to generate coherent 3D labels. And the second one is what kind of model can we actually use to perform zero-shot segmentation via text prompting, which was the demo that I showed at the beginning. So let's first talk about the model. It's actually very simple model, like most of the current architectures in segmentation. It follows the same trend of first, having your favorite backbone and then having an instance decoder that converts the object queries into essentially your masks. And of course, the backbone acts on the LiDAR point cloud directly, but you could also work on range images or whatever is your favorite representation, and it wouldn't really change the concept. Now, this gives you the instances, but it doesn't give you any semantics, right? So the semantics come from CLIP, as I've said, and they allow you to perform zero-shot classification. And in order to do that, what we do is we append a CLIP token into the prediction from our object queries that then we're going to align with the text encoder that is coming from CLIP. And so with that, what we can do is we can now basically prompt our LiDAR scans for any category and obtain a localization, so a mask of the object and the semantics. So another question is, okay, how do we train such this segment anything model? And specifically, how do we get the data to train such model, right? I mean, once I have this data, things are pretty standard, but how do I obtain this data without manually annotating a bunch of 3D scans? So here's where the SAL pseudo label comes in. So the SAL pseudo label is based on paired camera and LiDAR data, completely unlabeled, right? So these are just recorded. And what we do is we run SAM on the images, and then we do design projection from 2D to 3D, right? And we do this basically for all of the images of this like, multi-view setup. And so we have like a pretty good coverage of the LiDAR scan. You see here the LiDAR scan that is being colored essentially with the sun mask. And in parallel, we also, of course, have the clip features, right? So in the end, we're going to end up with this pseudo label plus the clip features. So what happens though if you stop there is that this unprojection from 2D to 3D creates a bunch of problems, creates all these like bleeding effects where essentially the mask of your car extends all the way into the background, into trees and buildings. And so in order to solve them, we need to introduce some information about the actual geometry, right? About the actual 3D information that is given in the LiDAR scans. So what we do is we just like very simply run dbScan. So it's a clustering algorithm that basically gives you clusters based on the LiDAR geometry. And then we basically fuse the SAM clusters with the dbScan. So we have the semantic information coming from SAM and the geometry information coming from dbScan. And merging both is actually what gives us tighter mask and good semantic. So these are going to be our pseudo labels, right? There's no more secret sauce here. And with this, we can do like cool stuff, like for example, segmenting curves. So you see like highlighted this part of the road and not the actual road where the cars are driving. Or we can also see, for example, streetcars. So you see this big streetcar that is passing by. Again, no temporal coherence, so we're going to have some flickering, but it's also highlighting that and not the actual cars. And so let's look at some results. I don't want to show too many numbers, but I think there's a couple of numbers that are interesting here. The first one is we need to compare our zero-shot baseline with a fully supervised baseline, right? We need to go to know how far we are. So note that this is basically the first zero-shot LiDAR panoptic segmentation baseline, right? So it's going to be bad by definition. But with the fact that it's not trained with any ground truth in 2D and 3D, it's already pretty cool that we can reach like more or less like half the accuracy of a fully supervised method. And this is for the default classes, right? If we now look at the columns on the right, for the super classes, we see that now the performance becomes much, much better. So here we have already the first hint that the semantic part is actually what is not working in this model. And so let's see why this is the case. So first of all, we need to check also that the model improves over the pseudo labels, right? I mean, we have a pretty complex pseudo labeling method. So having a feed-forward model that does that for you is already a benefit, but we also want to get better performance. And so here we see like that there's actually quite a difference in PQ where we have like 48.7 for the pseudo labeling model, while with our model we reach more than 70 in PQ, which means that your model is actually absorbing a lot of the noise that the pseudo labels have. So this is a really good thing, but an even better thing is that this 70.7 performance is very, very close to the segmentation of the fully supervised model. And here's the caveat. So here we're measuring the class agnostic segmentation, which means I'm just measuring how good my masks are, and I get my semantics from an oracle, which really shows you that the model has learned to do segmentation, and it's struggling a little bit with semantics. So from the segmentation point of view, I say we're good to go. We're comparable with fully supervised models. Now, another interesting thing is that sometimes your camera doesn't really cover the full 360 degrees. And so you're going to have parts of the LiDARs that are not really covered by the cameras. And so you're not going to have pseudo labels in there. So if you actually measure the performance of the pseudo labels, this is heavily impacted by this viewpoint. So you see this like really bad performance of 8.2, while our model has a much better performance because it has full coverage of the LiDAR scans. And how we actually obtain this is because we artificially create 360 covered LiDAR scans with pseudo labels, but just pasting different LiDAR scans on top of each other to cover the 360 degrees. Okay, so what happens though temporally? Well, temporally, it's pretty much a disaster, right? I mean, things are not stable. It makes sense. It's not a temporal model, but seeing this video really prompted us to say, okay, we really need to work on the temporal part and get a really coherent output. And especially for instances, we actually want to know what are the tracks of these objects. So once we did SAL, we went into the temporal part, right? Like getting this temporal coherence. And so here I'm going to show some of the initial results that we had, right, of this SAL 4D. And you see, especially if you look at the semantics part, which is what we were plotting before, you see that results are much more stable, right? So there's some flickering for some classes, like the other vehicle classes sometimes collides with the car class. But in general, the road, the curb, the trees are pretty stable. And so here, there's again these two ingredients, right? The model and the pseudo labels. And here I just want to highlight a little bit the problem with the pseudo labels. So here we have the ground truth for these two cyclists that are separated into two instances with two colors in the ground truth. Now, if we take the SAL pseudo labels, the 3D SAL, they're of course like divided into different instances for each timestamp, right? So there is no way to obtain a coherent 4D track, while the 4D pseudo labels are aimed at actually obtaining this coherent output. And so this is what we're going to use to train our model, which basically takes in the superimposed 4D point cloud for the whole sequence. Now, I don't want to talk too much about it because this paper is actually going to be presented on Sunday morning. So if you have nothing else to do, then please stop by the poster session number 5. Okay, so let's go to the third one. So I think this one is interesting because there's not much that we can do with the first two ingredients of the foundation model, right? So there's really a lot that we can learn when we have seen completion. And so this was the next project that we worked on, the complete anything in LiDAR. And here the idea is the same, right? You take as input a single point cloud and your favorite vocabulary, and as output you get instances and semantics, but also shape completion. So you can see here how we have the outputs of the cars, which are not actually partial, but you see the full shape of the car. And the same for the trees and all the other categories. So how do we go about this? So as I said, the input is a single LiDAR scan, right? But in order to obtain nice completed shapes, we need to see the object from multiple views, which means that our pseudo labels cannot really act on this one timestamp, but they really need to look at the full video, right? They really need to get as many views of the object as possible. So the pseudo label engine works on video object localization. So in this case, we basically extend from using SAM to SAM2. Then we do the same 2D to 3D lift and refinement. So we obtain the pseudo label for the LiDAR point clouds over time. And then we have, now with the accumulated labeled points, we have this kind of voxelized representation of the pseudo labels. Now, since these are still a little bit noisy, what we do is that we use the accumulated 360-degree LiDAR point clouds, right? We accumulate it to get these completed shapes, and together with accumulated pseudo labels, we can now get these refined pseudo labels through a CRF refinement. So basically, you get more completed shapes, and you get the clip features that we need anyway to do the zero-shot segmentation. So essentially what you're going to get is you're going to get these pseudo-label pairs in which you have a sparse LiDAR scan. And on the other hand, you have completed shapes and clip features. And now if you, for example, like do some zero-shot recognition via text queries, we have plotted here some of the similarities for these completed shapes. And you see in red where there's a high similarity, and in blue where there's low similarity. And you see that, for example, the truck is highlighted, and it's actually a different category than the car. And the road is also highlighted while all the other objects have a low similarity. So we see that this zero-shot recognition works really well also for completed shapes. So I don't want to go too much into detail with the model, so I will directly go into actually presenting some of the results. So these are results of completion plus masks we see in the second column. And you see especially how incomplete the scans are of the vehicles and how nice and completed the shapes are at the end of the pipeline. And now, like when we do the prompting with the categories, with the classic semantic categories, we get really nice definition and separation between, the road and vehicles, vegetation, etc. Now, what can we do then with such an amodal output, right? Well, the first thing that we can do is train a detector, right? I mean, a detector is always going to work better with completed shapes. And so we can do, for example, zero-shot model detection, and we can get not only like a partial shape, but we can get the full extent of the object, right? So here you see in the last column how we have these like nice and completed detections for vehicles, for cars specifically, and even for trees. Right? So you can get like the different instances of the trees. And the cool thing is that even if you see the car only from the front, if it's recognized as a car, it's going to give you the full extent. So this is a much richer output and a much more useful output. Now we also have some baselines that, well, unfortunately, they work really bad, I have to say. So you can see here, like the cars are like barely detectable, barely separable between them, while we get like really nice separated and completed shapes. And I think that the coolest thing is that most previous methods were working on this fixed set vocabulary completion. So they could complete cars, they could complete bicycles, but no one really did this open vocabulary completion, right? And what the method is inherently doing is it's learning to complete any shape without any type of semantic preference, right? So when you learn to complete cars, you also learn to complete all the other categories. So I think that's a really cool synergy that we're seeing here. So, okay, I've talked a little bit about the first three ingredients of our foundation model, right? We went from open vocabulary classification and localization towards 4D open vocabulary classification localization, and finally also scene completion, which is basically our goal for making this prediction really useful. And now you might think that I will talk about the foundation model part, but the title says towards a foundation model. And this is because we actually haven't done this last part, right? So still our models are trained on relatively small scale training data, and they don't really offer cross-sensor generalization. So we have worked quite a lot on domain adaptation, but this is a hard topic, especially in Lidar. And so our models is still like sensor trained for a specific sensor. But this is, I think, a cool research direction that we're working on right now. So, okay, just to summarize a little bit, with SAL and like follow-up works, we have presented the first proof of concept for zero-shot Lidar panoptic segmentation, which is both temporally coherent as well as a model. And all of this has been done without any annotations, right? Like no annotations on the image, no annotations on Lidar, just using the power of 2D foundation models. And the cool thing is that I haven't really shown results for that, but you can see that especially the semantic accuracy keeps improving as you scale with more data. And of course, as you scale with better 2D foundation models. Now, the bad things is that we have no generalization still across datasets and sensors. And we can only do transactive zero shot, right? Which means that if you haven't seen that object in the Lidar space, then you cannot really detect it and put a name to it. And so we're thinking about ways also to alleviate a little bit this dependency. You can always curate for more data. It's unlabeled data, so it's not really expensive. It's just the training time. But one could also do, for example, the semantic part with the 2D foundation models in 2D, right? And then the localization part with this pipeline. So this is also something that we're exploring. And here I leave you a couple of QR codes of the project website, and the code for this SAL and CAL will follow. And with this, I thank you for your attention, and I will take any questions.
Thank you for the great talk. I just have one question. You're using like the 2D foundation models that use like the images for SAM. And we have some like data set like semantic kitty that does not have like image data. So how do you think in this case we can use foundation models to have like ground truth pseudo labels?
Oh, this you cannot. I mean, either you start with Sal on Kitty data, right, and then you kind of bootstrap this. Otherwise, yeah, there is no. I mean, like if you want me to get creative, I could, right? I mean, you can generate the images with a diffusion model based on the lidar condition, for example. This is possible, but yeah, otherwise it's up to you to get this paired, and it's actually a pain to get the paired data, right? These are.
Yeah, excellent.
So yeah, thank you. Also, very nice talk. You said you were not reliant on any hand annotated data, and I think these foundation models can give you a lot of data. But if we gave you some tools that allowed you to efficiently annotate for the LiDAR sequences, would you have some use for that, for augmenting your data set? And if yes, what categories would be most interesting?
Right. So there's a couple of things that are interesting, right? Like one is actually finding the objects where you're really bad at segmentation or semantics, and then finding more data that contains those objects, right? Like this would be step number one. The second one would be actually improving the masks, right? But this is like, as we have seen right now, the actual segmentation performance is kind of on par with fully supervised methods. So here we don't see much of a need. Where we would need really help is on the semantic part, right? So really getting those pairs of here's what a car looks like, not a car, but like more like a rear object, right? For I think for cars, for pedestrians, things are relatively solved because there are many, right? I think for thinner structures, this is very problematic. So getting like good annotations there is crucial. Sometimes the pseudo labeling misses those thin structures. So this would be like an application where manual annotation is probably the only way to.
Okay, thank you.
Yeah.
Hi, thank you for the insightful talk. I have a question on if there were any post-processing steps that could be used from the pseudo labels to improve the semantics. For example, some kind of voting from clip across different images, and like, did you try that?
Like, to be honest, I think most of the improvement will come from actually merging LiDAR with images. Like this is fully on LiDAR, right? So the images are only used at train time, and at test time, you only have LiDAR. So of course, this is, I mean, it's harder to predict the semantics based only on geometry, right? And you cannot predict, for example, pedestrian crossings, things like this. So once we pair it with image data, I think the semantics will become much better. So this would, I think, be the obvious next step to improve.
Would that be like a multimodal kind of?
Exactly, exactly.
Hi, thank you for the talk. So I'm wondering, because in the real world LiDAR sensor, we also have a bunch of LiDAR noises, like the water splash, the dust point, or even the mirror point. You know, if we just projecting it to the image space, it may have some project the wrong pixel and have the wrong semantic meaning. So it may cause a lot of problems with pseudo label generation. Do you have any source of it?
Yeah, we do have that kind of problems, right? So what we observed is that basically all these problems can be found on the pseudo labels, right? So the pseudo labels are noisy, but as soon as you train a model on top, it basically learns to filter out the irrelevant noise, right? So this is the comparison that I showed, basically like from 48 PQ, we went all the way to 70 PQ. And this was simply comparing pseudo labels with the model. So I think much of the noise is actually absorbed.
Okay, so if you're trying to scale out the whole data set, do you think it's more benefit to just run the trained model to use that to refine the pseudo label again and then train the second time? Will that kind of iterative training be helpful?
Yeah, I mean, more towards finding new objects than anything else, right? So, for example, we don't need to train with more cars. Like for cars, it works, right? But once we, go for thinner structures or bicycles or even rarer objects, it would be nice to be able to know which sequences have those objects and then auto label probably with the actual model, and then repeat the process. But the actual curation of the data set will be done with the 2D foundation model. It makes no sense to do it in the LiDAR space.
Thank you.
All right. There are no more questions. Let's thank the speaker again.